Hi there, I'm Han, and this is just another video of me solving a random code problem. So then we have max stack. So we have to design a maximum stack data structure that support the stack operation and support the finding the stack's maximum element. So um, a similar problem to this gonna be the minimum stack. I suggest you check that out first before solving this because it is like very similar, almost identical, except we're gonna have like a pop max function here, right? So in the min stack, we are having like these four function, 1, 2, 3, 4, 5, right? Uh yeah, five functions, which is very similar, but we never have to pop the minimum, right? But now we need to pop the maximum. So previously we said that okay, in order to see the to do the peak max, right? We need to do it in O1, remember? And to do that, we are starting the minimum or the maximum up to a certain index, right? So -2, -2, right? Let's say we push in -2, 0, and -3, right? If we put in 0, so it would still be -2, right? The minimum still be -2, and we put in -3, so the minimum now is -3, right? Okay, so we're storing the value, the actual value to the minimum, right? Earlier, right? So we keep track of the minimum up to a certain index, right? So whenever we want to see the minimum, we can just look at the last element and the first index gonna separate, right? Let's say we pop this off, right? And the minimum will be updated to -2. Okay. Um. So that's just a quick reminder there. Um. So uh, now we need to retrieve the maximum element in the stack without removing it. Remove the maximum element in the stack and remove it. If there's more than one maximum element, only return. So if there's more than one um, maximum element, only return the top one. Okay, so it is required that we have to do it in O1 for each top call. Each top call, and then log n for each other call. Okay, so because we want to return the max, we want to be able to pop the max now, right? So we cannot just simply store the maximum up to a certain index, right? Because if we pop the max, right, and then all of the maximum value up to a certain index will be invalid, right? If we like remove like the first index, the first element in the stack. So to keep track of the maximum, we can use the heap, the data structure, the heap, right? The heap data structure, right? So the heap can be used. We can use the max heap, right? So for the max heap, right, it can deal with the pop max, right, and then the peak max, right, along with another data structure, right, which is our regular array stack, right. This can be used to deal with the pop and then the top, right. Okay, so instead of storing the maximum, right, up to a certain index, we need to store a unique ID for each element, right? Why? Because remember, if we are using a heap, right, the whole reason of using a heap is that we can look at the max, right, in O1 time, the peak max in O1 time, right? The peak max or the top, right, in O1 time, because we are required to be O1 for each core, each top core, right? So because the heap is unstructured, right? The heap is just a complete binary tree, And the invariant of the heap is that it is guaranteed that the parents always have a value greater than the children, right? And then we also have duplicate, right? So if we were to remove a maximum, right, pop max, then how do we know which maximum to remove, right? Because we have duplicate, right? And the instruction specifically said that we have to return the topmost one, like not just like any max, but like it has to be the max that's what added later, the one that was added later, the one that is closer to the top of the stack, right? So it is impossible to differentiate in the heap, right? We can differentiate in the stack, but it's just going to be like the last element. But in the heap, it is impossible to differentiate between two elements with the same value. So we need to give it each element an ID, right? So how do we store how do we figure out the priority inside the heap? How do we store the element? So we're gonna first like store by the ID, right? Sorry, the value, right? So if the value is uh greater, right? 6 could be at the roots, right? But if they have the same value, right? 6 and 6, for example, then we're gonna compare the ID, right? Whichever ID is uh greater will be stored at the root, right? So for example, if 6 have ID of 2, right? But the sticky only have ID of 1, which means this ID is being added later, right? We can just have a counter to count up the ID. Okay. So first, so the order in the heap will be stored in this priority, right? First, the value is greater, we have higher priority. But if the value is equal, then the one that is added later have a higher priority. In other words, added later mean have a higher ID, right? Because we're just gonna have a counter, right? Every time we add something into the heap, we just count it up by one. Okay. So that is our heap. Let's say we store 5 here. We push 5. We push 1. Right. 1, ID 1. And then 5, ID 2. Right? So we're just gonna increment the ID here, right? 0, right? 1, and then 2. Okay, as we add it to the heap. Okay, so the one at the root, right, will be which one? Will be this one, right? So another reason why we use the heap is that whenever we pop max, right, we can look at the maximum in constant time, right? But we can also pop the max in log of n, right? Right. So whenever we pop up the max, we have to swim down, right? We need to swap it with the last element, pop it up and then swim down until we put the last element into the correct place, right? So that is log of n to remove, right? But also remember that we also have the stack, right? So let's put it out here. So 5, 1, then 5, right? And we also have our ID, of course. So 0, 1, and 2. Okay. So when we pop up the max, right? In order for us to, let's say we pop up the max, right? Okay, easy, right? In the heap, just log of n, satisfy the requirement. But when we how are we gonna deal with this in the stack, right? Because we store our data in two data structure. It have to be in sync, right? So okay, we look at the stack. If we want to remove the max, we need to iterate through each and every single element in the stack, right? To find the element with this ID, right? We are searching by the ID, by the way, not the value, because we have duplicates, right? And then to find it, right, it's gonna take us O of n, right? It's not gonna satisfy the requirement here. So instead, we just not gonna do anything. We just gonna delay the delete operation in the stack as long as possible, right? And instead, we can just use a set, a deleted set, right? A set to keep track of the deleted node, right? Which is the ID2 here, okay? Because like if we find the element, it's gonna take us ON. So we're gonna delay this operation until later on, right? So let's say we just keep like adding and popping, right? And if we when if we actually deleted the max, right? So whenever we being the top is being called, right? If we are seeing we're gonna look at the last element, right? The top of the stack. So if the ID is inside the set, right? We're just gonna pop it out, right? Because popping off now is 01 because now we saw the elements, right? That we deleted earlier. So we can just pop it off, right? Earlier, if we want to delete, we need to search through the array to find the element with that ID. But now, if we were to, if we happen to see that this um, element, right, that we have been removed earlier is now at the top of the stack, right? We can just remove it now instead, but it is faster. It's only 01, right? Um, so yeah, so deleting from the heap, right, gonna be O of log n immediately, right, and O of 1 later on in the stack when we saw that element, right? So similarly, right, if we pop up the stack, right, if we call the method pop here, right? So we already solved the peak max, right? It's gonna be log n immediately, and then O of 1 later on when we saw that element in the stack, right? So the amortized high complexity gonna be log of n, right? For peak max, right? Peak max. Okay. So what about top? Sorry, pop. So when we pop it up, pop an element of the stack, right? Which is with whatever element at the top of the stack, you're gonna pop it up, delete that. So popping up is 01, 01 now, right? In the stack, right? 01. But we have another data structure. We need to keep it in sync, right? So the max heap is not shorted. It's not the max heap is not a binary search tree, right? The only invariant that we have is that it is a complete binary tree, and the parent is greater than the children. Um, if we want to search in the heap, right, we need to do it in O of n again, which won't satisfy the requirement. So we just apply the same strategy. We just delay it. We just delay this operation until later on where we really have to, right? So let's say when the peak max method is being called, oh, sorry, this is pop max, right? The pop max is log of n, sorry. I was, yeah, this is pop max. Pop is removing, pick is filling. So whenever we call the pick max method again, right? We're gonna check, right, the root, right? Where is the root? Is which is this one, right? It is have the same value, right? But a rater ID. Okay, so we're gonna check the root, right? Because pick max is looking at the root, right? Which is the maximum element. So if we see the ID at the root, right, is inside the deleted set, we're just gonna pop it off the heap, right, which is log of n, right? Right, because searching for the element to remove is n of n, right, and then deleted is log of n, right? But now if we wait until we saw that element later on when we call pick max method, right, the deleting now is only log of n because it is already at the root, right? We know where it is now, right? So again, for this is for pop max, right? And uh for pop, right? For pop, it is also log of n, right? For pop, this is gonna be O of 1 now, but O of log n later on, where we see that ID, that element in at the root of the max heap, right? Log of n, okay? And then pop max gonna be O of log n now, right? O of log n now, right? But it's gonna be O of 1 later on. O of log n now to remove it from the root, right? But it's gonna be O of 1 later on when we saw that element at the top of the stack, right, in our array. So the amortized time complexity is gonna be O of 1. Sorry, O of log n for the top method, right? Oh, sorry, for the pop method. If we don't account the time complexity of the pop inside the top, right? In the top method, right? In both top method, then our lookup gonna be only O of 1. Okay. So we already satisfied the requirement, right? O of 1 for each top call, and then O of log n for each auto call. So it is the amortized time complexity to remove an element, right? Again, if we remove a maximum element in the heap, right, which is at the root, it's gonna be log of n now, but gonna be over 1 later on when we see that element in the at the top of the stack. How do we know? Because we keep track of the deleted ID, right? If we pop, it's gonna be over 1 now because it is at the top of the stack. It's gonna be over log n later on when we saw that ID, right, at the root of the heap. Okay. And other than that, reading is just gonna be it's gonna be over 1. Okay. So that is our geometry there. So let's code this up. All right. So if you have a built-in heap in the language that you use, feel free to use it. Right. In JavaScript, I don't have a built-in heap, right? So I just gonna build my own here. All right. So first thing first, right? We need a deleted set equal to a new set. And then we have a stack. And then we have a max heap equal to new max heap. We can start out as an empty array. And the heap here gonna tag in a comparator function, right? So so that we can specify the priority in the heap, right? So as we said earlier, the A here, remember, gonna be a subarray, right? A subarray. So yeah, the A and B, the element in the heap gonna be the subarray, right? With the value to the ID, right? So the first priority, right, is that okay? A0. So if we're passing A and B, right, which means we are comparing A to B, right? When we add something to the heap, we need to swim up, right? Heapify up. We keep comparing to see if the element is greater than the parent, right? We can keep swapping it with the parent, right? So we only swap when the value is greater, right? If A is greater than B, A0 is greater than B0, right? So we are comparing the value, right? So if the value is equal, right? Then we're gonna compare the ID, right? Okay. So in other words, A is greater than B, if and only if A has a greater value, right? If A don't have a greater value and they have the same value, then A must have a greater ID, which means A comes later. It at the topmost of the stack. Okay. And we need to store our ID here to keep track of the count, right? Okay, so for push, push is pretty simple. Right? We just have to push it into the stack and the heap. This dot ID, right? And then this dot max heap dot push once x, and then this dot ID, right? And then we need to increment our ID for the next element. right? Pop. The remove element gonna be at the top of the stack, right? This is the stack of pop. We need to return the remove element, right? When we only want to return the value, right? So we look at index 0, not index 1. Index 1 is the ID, okay? And we need to add it into the set, the deleted set, remember? We only care about the ID here, right? So remember earlier when I said when we pop, right, it is O1 immediately when we pop up the stack, right? But it's gonna be O log n later on when we see that element in the root of the max heap. Okay, so and then for the pop max, right? For the pop max, it is O of log n right now immediately, right? Because we need to pop the element of the heap, right? So we need to swim down. So that is log of n, but it's gonna be O of 1 later on in the um stack, right? When we see that element at the top of the stack. So we need to check for the ID, right? Right. So the while loop here is for the later on step, right? If we saw the maximum element that we have removed earlier from the heap, that we have delayed until this point in the stack, right? Then we need to pop it out in O of 1 tab. Okay. So why the deleted set has last element, right? So this is the last element in the stack, right? Little stack of line -1. I mean, we're gonna look at the last element ID, right? Because you only store the ID in our set, right? Okay. So yeah, if we saw an element that we have deleted earlier in a max heap, right? Because we avoid searching, right? So that is open, we avoid searching. Now if we see it, we can pop it up in O1 tab, right? Because we are deleting this operation, the operation, right? The delete might never happen in most cases, right? So the amortized capacity is still O of 1 O of log n. Okay, so for top again, this is the opposite case, right? For the pop, right? We also need to do this, right? So pop is reading the top element of the stack, right? And then we want to read we don't want to return, we don't want to read the element that we already been deleted, right? So we need to check if the top of the stack, right, is if the element at the top of the stack has the ID inside our deleted set, right? If it is already deleted, then we want to pop it off. Okay, and then we can just remove this dot stack turn is a stack, right? And then this is a stack of line -1 and 0, right? Right. So after we pop it off, we pop off all deleted element, then we can return the value at the top of the stack. Okay, so for pick max, right, it's gonna be very similar to the top, right? Instead, we're gonna return the max heap, right? Support. So max heap support, if you will delete it and return the deleted element, right? Which is the root, which is the maximum. 0 here. Oh, sorry, it is a pick max, right? So we don't want to delete, we only want to look at the uh the root, right? The maximum. Okay. So so popping up in the stack, right? Gonna be O1 immediately, but log n later on, right? When we see that element at the as the root of the max heap, right? So now we just had to, before we returning the pick element, we just have to check, right? If the deleted set has the ID of the element at the root, right? We're just gonna remove it, okay? And then after that, we're just gonna return the root element values. So for pop max, very similar, okay? We have to make sure that the root is not one of the deleted element, right? And then we can delete that, and then return. We can delete that by return this dot maxif, right? Dot poll. So the poll gonna delete and return the deleted element, which is the root. And we're gonna return that its value, and then we need to put it in our set, of course. Okay. So we add the ID of the deleted element, right? So that we can delete it from the stack later on. All right. So that's pretty much it. Let's give it a try. Okay. Um. So let's see. We have pop. The first four element is the constructor and the push. So the top here, pop is good. Pop max is good. So the top is wrong here. So let's double check everything. So we are checking if the root of the heap, right, is one of the deleted value. If that is the case, we remove it, and then we delete the element, right, by calling in the massive poll. And before we delete, right, we want to store it into our deleted set so we can remove the stack later on. Okay, so this function looks good. Okay, we do the same thing, right, for the peak max here. And instead, we're just gonna return the maxi.peak 0, which is the value. Okay, top is really similar. We look at the top element of the stack. Okay, and then we look at index 1 for the ID. If that is in the stack, we pop it off the stack. Then we're just gonna return the value right at the top of the stack. Okay, looks good. Pop. Okay, we do the same thing, right? Check the top of the stack to see if it is test one of the deleted element. If it is, just pop it off. Otherwise, we can remove it by calling the pop method here. And then we add the ID into our set and then return the remove ID pusher. We're pushing in the value X and then the ID, and then we can increment the ID for the next element. Okay, looks good to me. So our set, our ID, our maxim. Okay. So we prioritize the value, right? And then the ID. Okay. So let's print out the heap, right? After we deleted the map to see what we have. So we have 50 as a root, which is not correct. Oh yeah, because we haven't removed it yet. Yeah, this looks like right to me. Ah, oh, okay. A typo here. Gosh. Right, now it worked. Okay. Oh, B here. All right, let's try it again. Okay. Yeah, thank you for watching.